Downforce. Probably the most important thing for a lot of different racing categories. Not all, but a lot of them. So that's what we're going to be talking about in this er8, the tech series. We're on episode 4 now. And yeah, I was contemplating maybe using aero as the title, but because that would include all kinds of different turbulence stuff, drag, and actually what we're really interested in most of the time is only downforce. So yeah, that's what this is about, and I'll do some historical references here and what sort of to do and what not to do. Of course, this is only a short YouTube video, so there's no possibility of doing a 40-hour long thing going through all the different possibilities and what to do and what not to do, but some cautionary stuff maybe in this video, and yeah, some generic guidelines also. So first of all, the very basics about downforce. First of all, there's this misconception that yeah, you create suction underneath the car, and that like sucks the car down on the road, like be that with the wings or the underbody of the car, or some other types of aerodynamic devices. But that doesn't really work, because with gases you can't have a negative pressure that I'm aware of, at least. I mean, you can in solids you can, and in liquids apparently you can. Well, I mean, it would be easy enough to test that for yourself, of course, but in gases I don't think you can have negative pressures. So by definition, if you create downforce with gases, then that's only because you have a higher pressure on the top surface than the bottom surface. So of course you're reducing the pressure on the bottom surface as much as possible, but you're of course limited by the ambient pressure and how much of a percentage you can get down from there. And on the top surfaces you of course want to create as much of a pressure there as possible, and on that you're limited by the flow velocity basically, and how high of a pressure you can reach by that. So yeah, well, what would we sort of be looking at? And yeah, also maybe a few misconceptions with the terminology. So there are a lot of people that use a flat floor in like very uncompatible ways. So some refer to a flat floor as like any type of custom designed floor that you have on your race car, and some regulations like use a flat floor name in that regard. But yeah, then there is the other kinds of definition for that would be to and that you see a lot of on the internet also, is to define a flat floor as a floor that is actually flat on the car, and that is just, I mean, incredibly horrible for aerodynamics, and you see lots of testing and people wanting flat floors, and this is of course very simple because people want to copy things that they see in other places, and okay, yeah, a GT3 car has a flat floor, and ooh, GT3 cars are very fast, so we want to copy that. Well, first of all, no, they're definitely not very fast. They have very poor downforce levels, and they only have a flat floor because the regulations mandate that. So why would you want to copy something that is bad because the regulations demand it, that it has to be bad? I mean, it just makes no sense at all. But if you do want to copy stuff, then I'll have some examples here that we'll go through shortly. But yeah, another aspect of the creating downforce. So yeah, you can. So yeah, downforce is created by pressure differences between the top and bottom surfaces, and then of course when you have a pressure difference, you have the surface area of that, or the surface area projection in the height dimension. So let's call that the z direction. So yeah, the larger the width and length of the area that you're working with and creating the pressure difference over, the more force you will have for the same pressure, of course. So yeah, you want to maximize that surface area. So you see all kinds of cars with these really, well, reasonably large like wings in front of the front wheels and these ginormous rear wings, but they're still like you're only like using like this much like space here, and the whole car is so much larger. So of course you want to use the whole car to create as much downforce as possible, and that is also in a way much easier to do because, well, with some innovation it's easier to do. So yeah, you see lots of small details on wings with all kinds of different end plate shapes and sort of end vortex protection, these lips, and lots of stacked rear wings with multiple profiles to maximize the efficiency of those. But the smaller detail levels you go into, it's much more complex to manufacture and also to design also and do CFD or wind tunnel testing on to some extent. So those are things to keep in mind when you look at this stuff. So we want to use the whole car as much as possible and not just like small individual pieces. Of course, everything is like well, not connected, but like the airflow around some part of a vehicle will have an influence on the rest of the vehicle also. So for instance, on our er8 here, we're definitely using a rear wing, not because the rear wing by itself is a very efficient way of creating downforce, but because with the rear wing we increase the flow velocity. So basically a free stream wing produces pressure differences by creating both what's it called in the correct terminology, so deflecting air and also creating velocity differences. So when you deflect air, of course air has a mass and moment, so you need a pressure, so a pressure to change the direction of the airflow, and you can of course create pressure on your wing surface by that means, and then also with the flow velocity. So when you speed up a flow relative to object, then that the surface on that object sees a lower sort of static pressure there. And yeah, so with typical wings, so you get a higher flow velocity on the bottom side of that wing, and slower flow velocity, and also a deflection of the airflow with the rear wing. And what we're interested in here is because you get a higher flow velocity underneath the wing, that means that we can increase the sort of stream velocity around the rear of the car, and then coupling that with the ground effect stuff, you can get a much more effective suction behind the car, and that will of course create, depending on how you have your ground effect set up, so you can create much higher flow velocities underneath the car, and then again reduces the pressure there. And if you keep the pressure on top of the car the same, or possibly even increase that, then you'll have a much higher pressure differential, and you can create lots of downforce very, very efficiently, or aerodynamically efficiently, and also design-wise very efficiently. But yeah, let's go look at some of the things that people copy. So some of the best examples available, they're not very recent though, but the Group C LeMans cars are, as far as I know, the most advanced ground effect cars that have ever been developed. So don't copy GT3 flat floor cars or like F1 aerodynamics or stuff like this. This is not a good starting point. Of course, the Group C cars also were reasonably limited with the rules then. So the floor and the front part of the car had to be flat, but you were allowed to have a free shape from, I believe it was between the halfway between the wheel axis rearwards. So you had a lot much more to play with than currently, but like limiting the first half of the car to having a flat floor is of course also very, very limiting. That there are a lot of racing categories that don't have these types of limits. So just something to keep in mind. And these are the type of cars we'll be looking at here. This is the rear wing of a Porsche 962 from, I'm not sure, from a 91, I think. So yeah, here you can see a typical rear wing section with multiple profiles here. And what is interesting is like this wing is not huge, very high up or anything like that. Well, it's not super low either, but the rear wheel arches here are reasonably in line with the wing. So this is, you have the wing and can create a high flow velocity underneath that wing. and like placing that correctly with the airflow, you can get a much increased or use that airflow velocity increase to get a higher suction from underneath your car, and that is what will really help produce lots of downforce. Where are we at? 10 minutes. Okay. Yeah, and this is maybe quite interesting car. One of the other aspects to note here is the height of the sidewall of the tire. This is a really good indicator of how much downforce cars produce and how fast they are, because once you start getting up to 300 plus kilometers per hour, then on high downforce cars, the downforce levels will be so high that there you have no possibility at all of running really low profile tires, because the tires will just be completely flattened basically by the amount of downforce. And once the tire gets very flat, the sidewalls start getting this too high of a sort of fold there, and then you will of course destroy the sidewall of the tires and have a unscheduled tire explosion at high speed. So yeah, if you see cars that have a really low profile tire and are claiming high top speeds and high downforce levels, then they're probably missing something or lying, or you have some artist's impression of the car or something like that. Just another thing to keep in mind. And yeah, let's look at, this is the Porsche 962, also DR2. So it has that had a flat six that a lot of Porsches of course run. So this is the rear of the car, and the front of the car is up here, and you have the slots for the rear wheels here, and this is like the bottom section, so the top of the car would be on the other side of this. And yeah, we have cutouts here for the half shafts apparently, and these second cutouts are probably for the lower A-arms, I would assume. And yeah, you have this large flat section here where you're not really possible, or you don't have the possibility of using these tunnel shapes and getting optimum area ratios, because the engine is basically blocking a lot of that tunneling, so you're losing a lot of potential here. But in this you can see these side tunnels reasonably well, so this is one of the sort of first design iterations that we actually, or something close to this, that we developed on the er8 also, to run sort of tunnels that are shaped sort of and curved outwards, so that you can get the maximum speed basically of air through these tunnel sections. And yeah, I mean it works reasonably well, but there is some further development that can be done on that also, that will greatly increase your downforce levels. And I'm unfortunately not going to go into any details on that, because that will have to wait till after a World Time Attack will go into the details on the aerodynamics on the er8. But yeah, just example to keep in mind here. Then one of the, I think this was one of the faster cars back then. I haven't researched this so much, so I'm not sure, but yeah, here you can see that the half shaft is moved up outside of this tunnel, so that will greatly increase the airflow quality there. And the less disturbed airflow you have, the larger the area ratio change you can have in the diffuser section. And that is of course very important, because the more you can slow down the air to the rear of the car, the more your sort of ambient airflow around the rear of the car will aid in the suction, and that will increase your flow velocity here underneath the front of the car and in the diffuser where you're producing downforce because of that. And yeah, unfortunately they still have a lower A-arm here inside the tunnel. Of course, well, yeah, you may ask, well, if it's the lower A-arm, it has to be there. Well, not really. In '93, the Nissan P35, apparently this wasn't a very successful race car, but it has some very well documented pictures and stuff. So by the way, yeah, all of these are on mulsandscorner.com. It's a very, very good website for all kinds of technical stuff regarding the Le Mans cars and aerodynamics and some engine technology also, I think. So I highly recommend visiting their site and checking out the details on all kinds of cars. I mean, from these historical Group C cars all the way to modern LMP ones. I think there are some technical descriptions of those. So very interesting stuff. Yeah, here on the front end you can see that the floor here is flat halfway to the car, about approximately at least. And for the front wheels you have a diffuser here, so this both produces a little bit of downforce here, with the diffuser in front of the front wheel, and it also helps slow down the airflow or the airstream that would otherwise be hitting or diverting around the bottom part of the front wheel, and that can produce some significant drag also. So having a diffuser there is really a good solution. Yeah, here is the rear suspension and diffuser on the P35. Yeah, it is still that one. So you can see the lower A-arm is brought up to the same height as the half shaft. So this of course increases the loading on the components, so they need to be stiffer and heavier, but your gains with the aerodynamics through the tunnel is so huge that it's, I mean, completely clear that is definitely what you need to do, even though you could run a much larger diffuser. But if you can't run the air through or run that as aggressively, then you're not going to have gains by running a larger diffuser. So that's yeah, one of the important things, and this is what they've been doing on some more modern F1 cars. I believe Red Bull maybe started doing that some 5, 7, 10 years ago, something like that, like bringing the suspension components in the rear up as far as possible to improve the airflow over the rear of the diffuser bodywork to again increase the suction from underneath the car. But in this same thing is used, but just so that you can increase the size of the tunnel instead. But I mean, both are for aerodynamic reasons at the cost of component weight. But for yeah, if you've seen the previous videos, I think it was maybe in episode 1, we went through the importance of things, and yeah, it should be clear to you guys that in most cases aerodynamics will trump everything. So if you need to compromise on suspension geometry or suspension components or engine placement or something like that to get more downforce from the car, that will typically help your overall performance. And yeah, here's another angle here on how these tunnels look. So yeah, they were using blown diffusers way back in '93 already, probably maybe even before then. But yes, you have the exhaust blowing in here, and that also yeah, aids in the air velocity underneath here, which of course increases the air velocity in the what is it, the narrow section there that is actually producing the downforce. So yeah, some interesting stuff. And here of course you can clearly see that all the suspension components are outside of that tunnel, so that greatly reduces the turbulence there. And even like having some small gaps for the through hole for lower A-arm, for instance, is really bad idea, because I mean, just the opening will already disturb the flow, but then having, of course, if you don't seal that opening somehow, that you typically can't do if you have a movable suspension component going through there, then the flow going through that hole, because of a pressure difference there, will upset that flow, and then you can't run the diffuser as aggressively as you otherwise could, and you end up losing lots of the potential from that. But yeah, and then yeah, so things not to copy. So copying Formula 1 aerodynamics, not so good, because those are based mostly on yeah, existing things that are designed specifically because the regulations are limiting you on what you can do. So this is, I mean, the Aston Martin Valkyrie, that is, I mean, one of the most interesting new cars that are coming out now, or I think it maybe has been released, of course, but has started delivery. Maybe, I'm not really sure on that. But yeah, you can clearly see from this that this is like heavily F1 based, this aerodynamic package. So you have a front wing here with a really high nose section, and this stepped tub section for the seating of the car, and really high sides, and yeah, from some different angles you can see they have like barge bores with the rear wheels. And so yeah, this is clearly using F1 technology to just copy things over, and you have all these what is these wake vortex sort of protection devices to keep the tip vortex there in a specific location and angle. And yeah, you have the inner edge here of the front wing stuff to produce some turbulence there that you want to guide through the back of the car and stuff like this. So yeah, this is a clearly F1 based thing, but But if you're doing a clean sheet project, then why would you use F1 technology? You would want to use these group C stuff type design, of course. But that's of course one of the interesting aspects is, of course, it's always easier to just do some improvements and use the knowledge you have instead of actually innovating. But there is a huge amount of potential to be had by innovating. So that is, I mean, if you're serious about really producing high amounts of downforce, then that's what you want to do. And yeah, here of course you can see the tire profile here. So this is by no means a super high downforce car, because they would need to have a completely different aspect ratio on those tires with a much higher sidewall. But of course this might just be some street tire or something like that, and they could potentially have like track day tires with a higher sidewall that will allow for more downforce at higher speeds. But yeah, who knows? But yeah, so those are some of the things that we've been thinking about with this. And of course, yeah, with modern CFD stuff, you can run, I mean, do so much more innovation and advancements and stuff. Of course, you always have to be wary about actually having useful data. So if you don't have any kind of tests sort of checking that the results you get from the CFD actually are meaningful in the real world also, then yeah, it's easy to get nice color plots and flow lines and all kinds of stuff, but that doesn't really mean anything unless you have some evidence that this is actually how the flow is behaving in the real world. I mean, even if in the wind tunnel stuff that they were in the Group C days, running thousands of hours of wind tunnel testing for the car development stuff, then even in those you have some with, because I mean you would run scale models. So with the scale model you have to have the Reynolds number the same, and then at the speeds they were going you also need to have the Mach number correct. So then you end up with the problem that you can't really use air anymore, or then you have to limit your testing speeds so that you're below the speeds where the Mach number starts affecting the airflow too much. So even in wind tunnel testing you have stuff that you need to really like be aware of and compare stuff with, so that you're actually getting meaningful results. But in CFD it's even more difficult. Even if you know what you're doing, it's very easy to get results that have absolutely nothing to do with the real world scenarios, because you can have like a tiny difference somewhere and the whole flow field will be completely different, and it's not like, okay, yeah, we're within 5% or something. Well, you can't be within 5%, but if you have a tiny error somewhere that creates a completely different flow field, then you can be off by 70% or something, and then doing a change in the model will not like correlate with the real world at all, because your whole flow field is completely different to what it would be in the real world. So yeah, those are things to think about, but it's not anything that is super difficult. I mean, there are probably some of you that are probably very capable and smart on this stuff. You can probably figure this out in, yeah, dedicate 2 weeks to looking at this, and you could potentially have a very good understanding on what kind of errors you might be doing and how to set up stuff. And there are open source softwares to do all this calculation stuff. But yeah, I think with some innovation you can do some huge gains, and I think that's maybe the main thing I wanted to say here. So yeah, we're doing some innovation stuff on the er8 and trying to understand how things work, and trying to do some correlation stuff and seeing if our understanding and our models and the meshes and things we use, so we're not using lattice Boltzmann with, would be better. But yeah, typical mesh stuff at the moment, because the software aspect is currently easier for that. Yeah, and with that we'll hopefully get some good results on this and see how it goes. But I mean, it's by no means like fully optimized or anything like that, so there are definitely going to be other people out there, maybe some of you people that have yeah, even better aerodynamic solutions. And in case I've said something completely wrong or something, then please leave comments below. I'll definitely check out all of those, and then we'll need to revisit this topic later, so then I can correct the errors that I made. Of course, some things are simplified, and some terminology I have definitely can't remember exactly what things are called. So those are of course things that are maybe something that please don't critique me too badly on that. But yeah, I'm Oscar from Elva Racing. This has been er8 the Tech Series, episode 4 about Downforce. See you guys in the next episode. Bye.